control system. Actually, it should be in previous semester, but time is not enough, and even this semester time will be not enough. So fire control system, it's common, some components for fuels, for power plant, and there are fire control system also for luggage compartment, for lavatories, etc. Natural gas system, no, I think this we have discussed previous semester. Ice protection system, also it should be partially in power plant systems, but time is not enough, and these two teams, number 4 fire control system and number 5 ice protection system, it will be for you for independent studying. So within course project, you can partially use this knowledge, so you can read this. Maybe you can read not completely all the sections, but all which you need. And two last teams we will occupy: environmental control system and emergency equipment. We will occupy this semester. So let's again turn to beginning, and let's start our first team, introduction to the core systems and equipment of aircraft. Initially, some general words. Some general words as course and this type of systems. Aircraft systems and equipment are intended for creation of acceptable or comfortable conditions for crew, passengers, and cargo. So, beautiful. Okay. 6 guys. So, protection against external action, safety provision, and sometimes for some special purposes. For example, fire control equipment for fire control aircraft, which must extinguish fire outside of the aircraft. Special purposes. Subject of our discipline systems and equipment of aircraft are functionality, design features, arrangement, evidence of operation of aircraft systems and equipment. Let's initially list what we should, in theory, discuss within this lecture course. Systems, hydraulic system. Hydraulic system is maybe the most important systems of airplane, hydromechanical system, which now provide power functions for almost all flight controls and for secondary devices which we need to control. It's like muscles of the pilot, big and powerful. Pneumatic system. It depends. In modern wood, pneumatic system usually is like interface between engines, which give high pressure air, and different consumers. With different consumers, it's usually in other systems. Fire control system. Here, I think you understand what is this. We need to track possible fire and stop it if it is appeared. Ice protection system. Unfortunately, in atmospheric of the airs, there are a lot of water, and this water can turn from gaseous state to liquid state, and from liquid state to solid state. So, overcooled water drops can turn to solid state on the surface of the aircraft and change this surface, change the shape. So usually this change turn to worsening of all aircraft flight performance. So to prevent them, sometimes it can be really dangerous, we use ice protection system, environmental control system. Must provide required conditions for the humans at high altitude, as for pressure, temperature, humidity, fresh air supply, because we breathe in and breathe out, and we could not breathe in what we have breathed out. So it's a very useful system. Without this system, it's a very critical system. Without this system, it's impossible to fly at high altitude. Of course, there are other systems, but they are mainly electrical or electronic. It's a subject of another departments. As for aircraft equipment, there is a lot of different equipment, so it's possible to mention furnishing, which is used for passengers, for flight crew. Unfortunately, this team is not ready. I didn't have time to prepare it. Emergency equipment. This team is ready and we will discuss it. It's maybe the most critical of them. So it's emergency oxygen system, emergency exits, inflatable slides and escape chutes, escape ropes, etc. So it's all kind of devices which are intended to allow rescue of the passengers during and after crash landing or ditching. All other which you see here, it's also not ready, so we will not discuss it in detail, but we can briefly mention what we should in theory discuss. Cargo handling equipment. It's typical for all kind of transport aviation. Even, I suppose you know, passenger airplanes have below the passenger deck so-called cargo deck for carrying special cargo pallets. So it's a very interesting subject, it's a mechanical subject, but sorry, I'm not ready to discuss it. Agricultural equipment. It's rather widely used for agricultural airplanes and helicopters to distribute pesticide above fields to improve agricultural equipment at ground and to help to grow vegetables, etc. So a special class of aircraft is used for this purpose, and it's also specific hydromechanical equipment. Well, fire extinguishing equipment for fire control aircraft, as I just mentioned. Sea equipment, which is used for amphibian and sea planes or helicopters. So it's very specific. It's anchor, water anchor, grapple, line and line through gun, etc. It's also interesting, but unfortunately, now I could not discuss it with you. I'm not ready. Next, some words about aircraft systems and equipment improvement directions. What's possible to do with aircraft systems and equipment to improve aircraft characteristics and passenger comfort, passenger safety? Sometimes it's possible to decrease mass of aircraft, firstly by decrease of mass of systems, which allows us to increase all kind of flight performance. Well, usually it happens vice versa. System mass not decreased, but system functionality usually increased because we make lighter usual components, but we add some other components which increase functionality. So it's such infinite process to increase functionality, reliability, safety, etc. So just see typical example here, it's overpressure in the hydraulic system. In the beginning of aviation, hydraulic pressure was about 7 megapascal, next 15, next 21. In modern wood you can see 28 and even 35. It's not accidental, it's just to decrease total mass of hydraulic system. There are more overpressure, there are less area of the pistons in the actuators required, and so total mass of the system usually decreases. Fire safe. Нас багато туди. Fire safety increase. Again, typical example, it's hydraulic system fluids which are using. So in the past, they very widely used flammable petroleum-based hydraulic fluids, which are very dangerous from point of view of fire safety. But in modern wood, a lot of years, all over the wood, in civil aviation first of all, military also, they use non-flammable working fluids, non-flammable materials as wide as possible for furnishings, for internal panels, etc. Application of anti-explosion systems, natural gas, we also mentioned previous semester. Crew and passenger safety increase. Here, first of all, it's emergency evacuation simplification and a means for survival after crash landing or ditching. So we'll discuss it in emergency. System's reliability increase. So all system has own features, but the most typical is duplication and redundancy. So it's also extra mess, but it's usually increase of safety, and safety should be first. Now, as for comfort, I think you understand that without environmental control system, it's impossible to fly. But even in this case, environmental control system can provide not only required conditions, but comfortable conditions. So, temperature interval can be adjusted more precisely. Humidity control allows you to avoid very dry air or very wet air, etc., etc., etc. So words about general requirements to aircraft systems and equipment from FAR CS 25. FAR 25, paragraph 1309, systems, equipment and installation tells us the following. The equipment, systems and installation, those functioning is required by the subchapter, must be designed to ensure that they perform their intended functions under any foreseeable operating conditions. So we should initially understand which condition we must withstand, and next our system should be designed so to withstand these conditions. B. The airplane systems and associated components considered separately and in relation to other systems must be designed so that what this paragraph says us, that not only system as a whole should be considered, but should be considered interrelation of systems which, by the designer's opinion, maybe should not interrelate, but they are arranged near to each other. And for example, leakage from environmental control system can overheat arranged near electrical system components or hydraulic system, etc. So such interrelation should be taken into account. So, 1. The occurrence of any failure condition which would prevent the continued safe flight and landing of the airplane is extremely improbable. So it's 10 in minus 9 power over flight hour. And the occurrence of any other failure conditions which would reduce the capability of the airplane or the ability of the crew to cope with adverse operating conditions is improbable. It is, if I'm not mistaken, 10 in minus 7 power over flight hour. C. Evident information must be provided to alert the crew to unsafe system operating conditions and to enable them to take appropriate corrective actions. Systems, controls, and associated monitorings and warning means must be designed to minimize crew errors, which could create additional hazards. It means misunderstanding of the conditions, misunderstanding of required actions, misunderstanding of actions which you actually begin to do, motion direction of the controls, etc., etc., etc. D. Compliance with the requirements of paragraph B of this section must be shown by analysis and necessary by appropriate ground, flight, or simulation tests. The analysis must consider possible modes of failure, including malfunctions and damage from external sources. The probability of multiple failures and undetected failures. So it means you discuss now one kind of failure, but maybe there is another failure which pilots were not aware. And so its combination can be very critical sometimes. 3. The resulting effect on the airplane and occupants considering the stage of flight and operating conditions. So the same failure during cruise flight, it's one case, but the same failure during landing, it's a little bit different case. No altitude, no speed, no time to cope. 4th, the crew volunteers corrective actions required and the capability of detecting faults. And the last paragraph E says us about critical environmental conditions for all these system applications. So if you say, for example, about electrical system components, operation at dry air, it's one case, operation at humid air, especially with a lot of salt water in the air, it's a little bit different case from point of view of corrosion. So environmental tests sometimes are very difficult to do, and sometimes they are really critical for selection of materials and for actions like coatings for these materials, etc. Well, that's with team 1. It's very small, it's introduction, and now let's start team 2, which is the biggest and one of the most important from this lecture course. So, hydraulic systems. Initially, we as usually begin from the purpose requirements to hydraulic systems. Hydraulic systems are intended for energy transfer from power sources to hydraulic actuators and for their control. So I said roughly hydraulic systems are muscles of the pilot in bigger plane. When pilot effort, muscle force of the pilot is not enough, we apply hydraulic system and it increases with muscle force of the pilot. And in this case, decreases fatigue of the flight crew. Requirements made to hydraulic systems are the following. First of all, here we mention design requirements which are not related to safety. Our next part says us about safety. So first, have enough power margin to perform all required functions. You imagine a situation when you deflect the control wheel, but ailerons could not be deflected due to very high dynamical loading. So it's a crash. Hydraulic system must have enough power margin to perform all required functions, sometimes simultaneously. You extend landing gear, in this case you need to control the airplane, counteract roll, for example. So it must be enough margin to do it. Otherwise it's a crash, immediate crash. No, some seconds. Next, keep operability independent on operating conditions. So airspeed, flight altitude, temperature, attitude, load factor, it's no matter. You must keep controllability of hydraulic system, otherwise it's also crash. 3. Have enough speed of force impulse transfer from control element to actuator. When hydraulic systems only began to use, it was a problem because if this impulse transfer speed is not enough, it leads to very specific problems in the control. You begin to deflect controls, but surface is not actually tuned to this position, and you deflect controls at bigger and bigger angles. Finally, surface begin to deflect. You see it's enough, but surface continue to deflect, and you begin to move controls in opposite direction. So this situation very often can lead to crash, especially at critical flight modes near to takeoff or landing. So it was a big problem when hydraulic systems only begin to apply in flight control system. Now all these problems in theory are solved, but sometimes it can happen. Next, have small mass and volume. It's desirable, but you see small mass for system which provide power function. It's of course defined by strength. So here mass will be maybe not so small as we wish. Small volume, yes, it's of course desirable. 5th, be simple and reliable. It's desire. It's almost impossible to say about modern aircraft system, no matter which system, to say that it is simple. It's desire. All the systems are very complicated. To say reliable, yes, we apply a lot of designers' effort to make hydraulic system as more reliable as possible. 6, have high power efficiency. Here they say not about power, but about power efficiency. So we should use effective hydraulic power sources, and just this it's the main. Minimize hydraulic power losses in the pipelines, etc. Have minimal maintenance and repair time and cost. It's also desirable, but you see that it's not so easy because modern structures are complicated, expensive, and it is not so small. It's minimal, but not so small. And now for requirements. Element design, paragraph 1435. First, element design. Each element of the hydraulic system must be designed too. And here we see practically critical load conditions, but they are very specific for hydraulic system components. First, withstand the proof pressure without permanent deformation that would prevent it from performing its intended functions, and the ultimate pressure without rupture. You see that proof pressure is something one, but ultimate pressure is something bigger. The proof and ultimate pressures are defined in terms of design operating pressure as follows. So it's possible to give such analogy. The design operating pressure, it's possible to compare with static loading for the wing, for example. Static loading in level flight. Proof pressure, it's possible to compare with limit loading. Ultimate, of course, with ultimate loading. So between the operation pressure and proof pressure, in theory it's load factor, here it's a factor, not load, but factor. And for ultimate pressure, it's also a factor like a safety factor, but another factor. This table shows you these factors. They are different for different components of hydraulic system. For tubes, for vessels, hoses, and for other equipment. Second, withstand without deformation that would prevent it from performing its intended function, the design operation pressure, in combination with limit structural loads that may be imposed. Third, withstand without rupture, the design operating pressure multiplied by a factor 1.5 is just safety factor, in combination with ultimate structural loads that can reasonably occur simultaneously. And the last one here withstands the fatigue effects of all cyclic pressure, including transient and associated externally included loads, taken into account the consequences of element failure, and perform as intended under all environmental conditions for which the pen is certified. So environmental condition, it's temperature, it's pressure difference, the same when we say pressure in hydraulic system, it's ground, but at high altitude it will be greater. So pressure drops with high altitude. Humidity, so corrosion, etc., etc., etc. B. System design. Each hydraulic system must have means located at a flight crew station to indicate appropriate system parameters if it performs the functions necessary for continued safe flight and landing, so for normal operation. And second, in the event of hydraulic system malfunction, corrective action by the crew to ensure continued safe flight and landing is necessary. So what to do in case of malfunction. Second, have means to ensure that system pressures, including transient pressures and pressures from fluid volumetric changes in element that are likely to remain closed long enough for such changes to occur, are within the design capabilities for each element, such that they meet the requirements defined in another paragraph. Third, have means to minimize the release of harmful or hazardous concentration of hydraulic fluid or vapors into the crew and passenger compartment during flight. Why it is important? Unfortunately, in modern wood, specific requirements to hydraulic fluid, usually requirements of fire safety, turns to situation when modern hydraulic fluids are toxic. So we must prevent this the fluid or vapor getting to the crew or passenger compartment. So it's really dangerous. Fourth, meet the applicable requirements of some paragraph if a flammable hydraulic fluid is used. So it's requirements for flammability. I said that in majority of cases we now use inflammable hydraulic fluids, especially in civil aviation. And fifth, be designed to use any suitable hydraulic fluid specified by the airplane manufacturer, which must be identified by appropriate marking as required. So it's first of all marking near to servicing connection points on the aircraft, but there is also marking by colorant. Specific fluid in domestic practice is marked by specific colorant. So you can see by color what is the leakage. Is it a hydraulic fluid or it is something else? C. Tests. The tests must be conducted on the hydraulic systems and all subsystems and elements except that analysis may be used in place of or to supplement testing, where the analysis is shown to be reliable and appropriate. So they means to save money for real tests if you can refer to previously certified components first of all, so it's possible to analyze it. All internal and external influences must be taken into account to extent necessary to evaluate their effects and to assure a reliable system and elements functioning and integration. Failure or unacceptable deficiency of an element or system must be corrected and they sufficiently retested. They are necessary. So again, they mean that we must create all ground facilities, branches special, which will simulate all kind of flight conditions, vibrations, temperature, overpressure, deformations or something else, and test it. In case of some failures, we must improve it and test again. Or we must provide flight tests, which are maybe more expensive and more dangerous, but close to real conditions. So the system, subsystems or elements must be subjected to performance, fatigue and endurance tests, representative of airplane ground and flight operations. Sometimes ground operation can also be critical. The complete system must be tested to determine proper functional performance and relation to the other systems, including simulation of relevant failure conditions and to support or validate element design. And third, the complete hydraulic systems must be functionally tested on the airplane in normal operation over the range of motion of all associated user systems. The test must be conducted at the system relief pressure of 1.25 times the design operating pressure if a system relief device is not a part of the system design. What does it mean? It means we can have in the hydraulic system special relief valve, and if this relief valve have failed, we should test our system with design operation pressure multiplied to this factor, so to simulate these conditions. And one more specific mechanical feature, clearances between hydraulic system elements and other systems or structural elements must remain adequate, and there must be no detrimental effects. It's actually a very critical feature. You see, hydraulic system components, first of all, pipelines, sometimes can be done of aluminum alloy. So they could not withstand contact stresses or friction with other elements, especially with sharp elements. So in case during deformation of assembly, aircraft assembly, or pipelines or something else, they come in contact, so destruction of aluminum pipelines, it's a question of minutes or hours. And finally, it's a leakage. If it is flammable substance, it's fire. If it is non-flammable, in any case, it's loss of hydraulic fluid, so it's loss of control of aircraft. It's very critical. Well, let's now discuss, first of all, features of different systems which can be used for the same purpose. Let's think what kind of systems we can use to simulate more powerful muscles for the pilot. It can be electromechanical system. It can be hydraulical system. It can be pneumatical system. Let's try to compare the advantages and disadvantages to understand why in modern wood hydraulic systems are used the most widely. You see the table, when in the left column you see parameter, and next three columns shows us three different systems and values of parameter or its estimation. Impulse transfer speed in meters per second. Not quite clear in electrical system, it's speed of light, it's the highest speed in our physical wood, so nobody can compare. It's the best. But for our purposes in hydraulic system, speed of sound about 1000 meters per second, it's quite enough. Even in the gas pneumatic system, speed of sound about 300 meters per second, it's also enough. Minimally, it's enough. Because size of airplane is not so huge to say it is big. Features of systems. Значит, electrical system can be alternative or direct current. And problems of this system, first of all, it's insulation. So destruction of insulation can result to very dangerous consequences. High voltage control and also cooling. So overheating of electrical equipment, it's quite normal, unfortunately. So overheating can also result to fire, to destruction, etc. As for hydraulic and pneumatic systems, here common features. There are hydrovolumetric and hydrodynamic systems. A little bit later we'll discuss what's this, I think today. And problems. Here problems, first of all, are related with operational fluid parameters and its filtering. Because it's natural liquid which we only absorbed for this function, and so its features, of course, we select such liquid which is the most suitable, but its features, its properties, some of them can be most critical, some less critical, and sometimes not possible to select such a fluid which will satisfy all our requirements because it is chemistry, and we could not create such a fluid which will meet all our requirements. Elasticity models. No, for electrical system it's not considered. For hydraulic system it depends. It depends of content of gas inside them. Fluid from 300 to 2000 megapascal. For pneumatic system, it's adiabatic coefficient multiplied to overpressure. No, taking into account that overpressure in pneumatic system it's about 1428 megapascal. So multiply 28 for 1.4, it's about 40 megapascal. So it's 100 times less than in hydraulic system. So it's of course better. Relative starting time. Here we assume as a unit electrical system starting time, and hydraulic system will start far slowly, about 30,000 times slower. Pneumatic about 1 million times slower. So from this point of view, electrical system is the best. It seems that stopping time should be the same, but it's vice versa. Why so? Pay attention, electrical system usually have electric motors, electric drives, rotary. And they have very big moment of inertia, so will be big inertia to stop it. So for electrical system, electromechanical system, and for pneumatic system, almost the same time. Hydraulic system about 10 times better to slow the time for stoppage, so it's very good. Relative mass of components of the system. Power sources. Power sources for electrical system, it's electric generators on the main engines, and they are rather heavy. Power source of hydraulic system, it's hydraulic motors. As you see, it's about 10 times lighter. And for pneumatic system is compressors. They are also very heavy, which is why they are almost never used in airplanes, but rather widely used in helicopters for off-aerodrome bathing. Hydraulic actuators. Actuators figures, you see different dimension here. For electrical components, it's very big because there is a electric motor, there is reduction gearbox, so totally it's rather heavy. Hydraulic system almost 7 times slower. Pneumatic system usually a little bit lighter. Feature of pneumatic system, but comparable. So hydraulic system also here is very good. Lines. Electrical lines, it's the cables. They depend on required power supply. It may be light, maybe rather heavy. Hydraulic system has small, but a little bit greater than minimum here. Pneumatic system usually twice less than hydraulic. Why? Hydraulic system has power line and return line. In pneumatic system, we have power line and have no return line. Gas exhausted to atmosphere, which is why here figure twice less than here. But if you compare with electrical, it's possible to say that it depends, but in most conditions, hydraulic systems are very good. Accumulators. I think you know that electrical accumulator is rather heavy device, electrical battery. But it's maybe shocking for somebody, hydraulic accumulator is heavier. Even pneumatic accumulator is rather heavy, so heavier than electrical, but it is also used. System efficiency, it's 60-70%, 70-90% in hydromechanical system. Limit frequencies. So it's limit frequencies when we have reciprocating motion of actuator. Here, of course, electrical system have a benefit, but hydraulic system usually enough from this point of view. Так, what we have? We have bell. So let's have a break. I will call the roll. Так, это у нас Aircraft Systems and Equipment. Так, Allen Paul Saravanan. Yes, I see. Мадуйки Чебуйкен. Yes, I see. David Daniel Titus. Okay. Demi Гуннике. Не понял. Ага, yes. Гунника добавляю. Так. Что у нас там дальше? Peculiar. Окей. Себастьян Белла. Белла. Окей. Ванитха. And Zahir Abbas. So, Ravi Chandran sign cash is absent. Am I correct?
Yes, sir.
Yes, sir.
Okay, let's have a small break. Она написала вчера, что не хватает правды. Раньше тут была кнопка. Заходил сюда, и тут была кнопка «Включить запись». А как? Где? Тут вообще даже нет упоминания запись. Где-то тут еще была кнопка «Включить запись». Короче, нет. Как потом доказывать, что они приедут? Я вчера открыл приложение, можно ответить, что у вас нет прав. Вот настройки видео.
Тут надо, наверное, разрешить создание файла.
Так, ну, let's continue lecture. Так, next what we should discuss here is fire hazard. Feature of electrical system we discuss its problems with insulation and problems with cooling, so overheating. As a result, it can result in fire. So special means required which increasing mass of the system, cost of the system to prevent this or to localize it. In hydraulic system, if you use non-flammable fluid, there are no problems with fire. Even in pneumatic system, we can use not air but nitrogen, which doesn't support fire. So in this case, fire hazard is absent. No hazard. Influence of electromagnetic fields. In electrical system, it of course influences especially to control functions. But in hydraulic and pneumatic system, no influence. Survivability. Here it depends. When we say about line broken, in electrical system, no problem. No, if one line is broken, we can foresee another line and we can supply power from another line by switch or something else. No leakage of the electricity in atmosphere through the broken line. This is benefit. In hydraulic or pneumatic system, it's just a problem. In case of line broken, we must foresee special devices, special means to terminate leakage. Otherwise, we can lose all the hydraulic fluid or all the air from the bottles, and there will be no possibility to control the airplane. Reduction gearbox presence. In electrical system, it almost always present. It's a feature of electrical components, electrical motors, generators, that they are effective just with very high frequency. And to convert with high frequency RPM to low frequency RPM, we require reduction gearbox. So total mass of electric actuator plus gearbox is lower than total mass of electric actuator for low speed. But in hydraulic system and pneumatic system, the most often we use linear actuator, and no reduction gearbox required. So it makes it simple, makes it more reliable, and easy in maintenance. Exactness or precision of positioning of object of actuation. In electrical system, it's low due to inertia. In hydraulic system, it's high, and it's just the main advantage which is used to deflect control surfaces, which allow us to deflect it precisely as we wish, just at small motion or at high motion as pilot design. In pneumatic system, no exactness due to compressibility of the gas. Sensitivity to stoppage under loading. It means situation when external power or force exceeds power or force of the hydraulic of the actuator. For electrical system, it can result to failure because of overheating. So it's really critical. And for hydraulic and pneumatic system, no problem with this. And the application of duplicating or redundancy. In electrical systems, it usually results in rather complicated structure. In hydraulic and pneumatic system, it's no problem from point of view of hydraulic or pneumatic. There are, of course, problems from point of view of mechanical connections, but it is solved and it is well known how to do it, so all over the wood this problem was solved. Let's take a look to these systems from a little bit different side of view. Let's characterize each of the system as advantages, disadvantages, and areas of application. Electromechanical power drive systems. They can transfer high power practically instantly. No, for length of the airplane, speed of light, it's almost infinite speed because 300,000 kilometers and length of airplane, it's incomparable distances. So it's very good. Electromechanical systems are convenient in installation and maintenance. So when they are de-energized, they are safe. You could not have a leakage of something. It's no overpressure. It's easy. Only electrical connections, USB and something else. They have high survivability. So from point of view of leakages. As disadvantages, necessary to mention, big mass and volume. No? Feature of electrical system, copper alloys usually heavy. Big inertia and low stiffness, we discussed it. Have relatively high cost of units. So do you see electronic which is not expensive? Almost no. Have problems with cooling, we also mentioned. Have insulation problems, especially at high altitude. You see, sometimes inside the devices we can have insulation, no insulation. Insulation as air space, air gap. But with air density change, with high altitude, air density decreases. Insulation of this air gap decreases. Resistance decreases. And so we must have bigger distance or increase of size or apply special material for insulation. So they are used for low power drive. When it is really low power, it's maybe effective. For the power drive not sensitive to inertia and stiffness, something auxiliary, not flight control surface, something else. And remote control of the other drive type. For this purpose, electrical system is used the most widely. And also redundant or emergency systems. Yes, it's sometimes very effective because of small size and for low power. Hydraulic system. Advantages. Have low mass. Have high power and unit of volume. Can provide short-term high power by hydraulic accumulators. So even if we have hydraulic sources, primary sources broken, hydraulic accumulator can provide some additional power for short time. They are efficient and reliable. Have enough stiffness and speed, we mentioned it. As for disadvantages, have not enough temperature interval, it's a features of working fluid. Can have leakages in connecting places. So it's a problem, leakages with high pressure. And you see, in modern wood, to decrease mass, we usually increase pressure. When we increase pressure, leakage problem increases also. Have actuator sensitivity to working fluid purity, so filtration required, and it's a big problem. So they are applied in high power drive with strong loadings, stiffness and speed requirements. So it's primary flight control surface and usually secondary flight control surface. Pneumatic power drive systems have the minimal mass, a little bit lighter than hydraulic. Have the best working fluid property stability. It's a gas here, not so big problem. Have the best fire safety. Gas flammable, we will not use flammable gas. Have no duties. Can transfer high short-term power. As for disadvantages, have low power and unit volume due to compressibility. Have problems of gas because of gas compressibility, so it's no fixation in the middle, no exactness of the motion. Have different difficulties with pressurization. So It's also like a leakage, and are subjected to condensate appearing in system volume. So if we use atmospheric air, it can contain moisture, and with moisture can cause corrosion, can change some other properties of the gas, so it's problem. They are applied in low power drive systems. In the past, it was used very widely. Now it is used as a power drive, maybe in some agricultural airplanes or some helicopters, something light or something old. Remote control of elements. It's usually emergency or something light or agricultural. Short-term or one-power drive, usually emergency, yes. Redundant or emergency systems. For example, emergency exits all over the wood in airplanes are usually opened in emergency by pneumatic system. So fire safety in this case and independence from anything else. Well, now some words about principles of operation of hydraulic and pneumatic systems. Hydraulic systems are subdivided, as was mentioned above, to two classes, hydrovolumetric and hydrodynamic. Let's discuss hydrovolumetric systems. In this case, working fluid is used as a geometrical constraint between input and output links. Such system works analogously to mechanical level. Let's look to picture 1, this picture. Here you see mechanical level, when there is level L1 and arm L2. Force R1, force R2, and it causes motion X1, angular motion, and angular motion X2. From mechanics, you remember formula for correlation between angular motion. X2 is X1 to ratio of arms, L2 L1, and force R2, which we get in the opposite arm. R1 it's input, R2 it's output. Force R2 will be equal to force R1 multiplied to levels of arms ratio, but inverted, L1 over L2. In the hydrovolumetric system, you can imagine common vessels and pair of pistons. One piston is hydraulic motor, another piston is hydraulic, one piston is hydraulic pump, another piston is hydraulic motor. So here there is reaction, those input reaction R1 and output R2, and motion X1, X2. How to get correlation between them? Let's take a look to this formula. We now continuity of volume. So volume is which is displaced from the first cylinder is equal to its area, cross-section area multiplied to motion x1. In this case, it's linear motion. And this volume must be equal to volume which appeared in the output cylinder. So it's its cross-section area multiplied to its motion x2. And from this equation, you can get x2 equal to x1 multiplied to ratio of diameter squared. And to discuss loadings, we can say that according to hydrostatic, pressure here is equal to pressure here. So pressure here is equal to force R1 over the area, pi d1 squared over 4. And it is equal to pressure P2 here. It's force R2 over area of second piston. So from this equation, it's possible to get a reaction R2 as reaction R1 multiplied to diameter difference squared. And you see analogy. It's a little bit different coefficient, but the main input and output units of the hydrovolumetric systems are kinematically connected with working fluid. Any pressure in the system is determined by external action acting on the output valve. So hydrovolumetric systems are very widely used in aviation, and usually they are precise, fast, and follow-up systems. Some words about hydrodynamic systems. They have analogy with mechanical gearing or toothing. If you have pair of gears interconnected here by some couple of tools, you have here diameter 1, diameter 2 of the gears, and angular motion angle phi and phi1, phi2. A kinematic relation you see, and a relation for the torques you also see here. Hydrodynamic system, what is this? It's a combination of pair of van machines, centrifugal pump and circumferential hydraulic turbine. Their working wheels are placed near to each other at minimal distance and concluded in a common case with alignment. When pump wheels rotates, with pump wheels is rotated by external power. Fluid gets on the turbine by inertial force due to shape. And fluid, which is rotated together with pump wheel, forces turbine wheel to rotate in the same direction, usually with the same speed or similar speed. So power is transferred without rigid constraint. And we have rather complicated dependencies for angular speed and for moment its function. It's not so easy as in mechanical analogy. It's possible to mention as advantage of hydrodynamic system that if output shaft is subjected to strong contact loading, to strong vibrations, to possibility of to be destruction of this strong loading. Just with hydrodynamic coupling allows to save input link, input shaft against all kind of loading. Hydraulic fluid will damp with loadings, impact loadings, vibrations, etc. So in aviation, hydrodynamic systems are used extremely seldom, but where necessary, you sometimes can find them. Well, general features of aviation hydraulic systems. About 20-30 functions, so actuators, are provided by one hydraulic motor, which results in a very big complexity of the system. So hydraulic systems of airplanes are rather complicated. When you see in flight manual, you see usually simplified system. And even in this case, it looks not so simple. A real structure is more complicated. To provide high level of flight safety, critical actuators are reserved, sometimes up to 3-4. It means that results in complicated multi-chamber flow-up drives creation. What does it mean? It's possible to see at one primary flight control surface 2, 3, or 4 actuators attached to different hydraulic systems. Next, to increase survivability of manned aircraft, critical subsystems can be connected to some independent pumps and in turn be reserved by pneumatic or electromechanical power sources. For example, landing gear extension can be done normally by hydraulic system, maybe by one, maybe by second, maybe by third, in case first or second have failed. And in addition, maybe standby electrical system or pneumatic system to extend landing gear. Next. To meet wide temperature, altitude, and aircraft attitude operation condition, it's necessary to use some special solutions. We will discuss them in specific features, so closed type system, heat exchangers, etc. All this also makes the system more complicated. Aircraft and engine control subsystems work by complex algorithm, which results in automatic electro-hydraulic control units creation. So in modern wood, you could not now say hydraulic system, it's hydromechanical. It includes a lot of electrical components to control hydraulic, and in this case, it is interconnected with electrical, with electronic, because algorithms are really complicated. To minimize mass and volume of units, it's necessary to apply maximum possible working pressure allowable by existing materials and sealants. Okay, now let's discuss some terms which we use in this hydraulic system. Structure and classification of hydraulic systems. The main units of volumetric systems are power sources. Power sources, it's different kind of pumps. It's usually displacement type pumps, so in other words, volumetric pumps. We will discuss them in detail what's with a little bit later, next time. Drives. Drives, it's another word, actuators. So it's devices which are directly connected to actuating object, to control surface, to landing gear, to doors or to something else. Drives can be reciprocating, it's usually cylinders, the most often. They can be rotary drives or hydraulic motors. Not so often, but all the flaps, slots, stabilizer are controlled by hydro motors. And angular drives. No, angular drives, it's exception. I never see its real application. Directing units. So it's shut-off valves. They control fluid by full open or full close position. They are usually solenoid valves or electric motor shut-off valves. So, or full open or full close. It's only two position normal, or other transit. Regulating units control fluid pressure and flow by partial open or flow area. It's reducers or more often pressure regulators and control valves which allow partial opening in normal state. It's a little bit different. And some auxiliary units. No, it's impossible to say. It's possible to say with units are auxiliary, but it's impossible to fly without them. Filters, accumulators, tanks or reservoirs, heat exchangers, pipelines, inspection tools. So it's very important devices, even if they have such a name. Well, let's now give some definitions. Hydraulic system. Finally, we come to definition what we are studying. Hydraulic system. Hydraulic system is a set of interacting units transferring energy through working fluid, providing consumer by energy, transferring it to mechanical work, and controlling consumer's operation modes by pilot or automatic control system actions. Rather long definition, but rather common. Functional subsystem. We say hydraulic system on the aircraft, but inside hydraulic system it's possible to select functional subsystems. Functional subsystem is the hydraulic system or its part serving one consumer. They can be continuous, event or action, follow-up, relay type, etc. What does it mean? Functional subsystem for aileron control. Functional subsystem for landing gear control. Functional subsystem for wheel brakes control. Functional subsystems. Hydraulic units is any hydraulic system component performing own function in it, such as working fluid properties or flow parameters change or react to these factors. So hydraulic unit, it's any component which we discuss in the hydraulic system. So when we say about component, we say hydraulic unit. Consumer. In this case, it's a device which apply hydraulic power to mechanical power transfer. Usually it's actuator with linear or rotary or something else. So it's with actuator is directly connected to object of actuation. So aileron, elevator, landing gear leg, wheel brake or something else. They distinguish some hydraulic system types depending on features of hydraulic system. They distinguish open type hydraulic system. It is a hydraulic system which keeps working fluid in direct contact with air in hydraulic tank. So, like in fuel system, we have open venting system. Open, it means with atmosphere we have open venting. Maybe it's overpressure, but it's air. It's not any other special natural gas, and it is not something else. So in the past, all kind of hydraulic systems were open. Some 10 years ago, abroad, they turned to another type of system, and you see now something else. Closed type hydraulic system, what with more modern type. It's a hydraulic system which insulates working fluid from direct contact with any gas in hydraulic tank. Hydraulic tank structure will be very specific, like fuel accumulator. It will be piston, which separates hydraulic volume from gas volume or any other kind of volume, but hydraulic fluid now is insulated from contact with gas. So less quantity of gas turns to a dissolved state in the fluid. It's good. From this point of view, it's good. And in modern wood, almost all modern aircraft has closed-type hydraulic system. Semi-enclosed type hydraulic system is a hydraulic system which keeps working fluid in direct contact with natural gas in hydraulic tank. So instead of air, which supports combustion, they use usually nitrogen. So in the past, it was important when petroleum-based fluids were used, and so to avoid fire, it was important, especially in supersonic airplanes. But when they turned to non-flammable fluids, this problem was avoided. And now such systems are not used. Centralized hydraulic system. It's a system which serves a group of consumers. So imagine you have one hydraulic pump and you have two actuators, as minimum two or more. So it is centralized system because more than one actuator in the system. Self-contained hydraulic system serves a single consumer. So there is a pump and there is one actuator. But this is self-contained hydraulic system. It seems it's bad, but it's vice versa. In modern wood, self-contained hydraulic system, I think it's the future of hydraulic system, and it allows to localize leakage. So to stop this main problem of hydraulic system. Next, a main hydraulic system. It's a system which serves consumers in normal operation. For this consumer, the system is main. Standby hydraulic system serves some consumers as main one, but can be connected to another consumer if necessary. And for this another consumer, it is standby. For example, one student making his own homework. Another student should make his own homework, but with another student ask first to help. It is standby for second student. No, it's of course joke. Emergency hydraulic system operates in emergency only. So, see difference. Standby system has own actuators, normal. But emergency system have no normal actuators. It's extra weight in normal cases. It waits for emergency. And only in the emergency it activated and begin to work. In modern wood, it's difficult to find emergency systems. Usually they are main and standby. And one more important definition, multiple hydraulic system. They serve redundant consumers during normal operation. They can serve other consumers independently. Imagine, you have 4 hydraulic systems on board aircraft. For this specific control surface, you have 3 actuators. Each of them connected to different system, of course. So these are multiple hydraulic systems. For this actuator, first, second, and third systems are multiple. Fourth is not used here. And the most often term which we use very often, independent hydraulic system. I wish that you remember now what's this word mean. Independent hydraulic system serves a group of consumers and do not connect it to other independent system in case of failure. Before it was definition self-contained hydraulic system. By the words they are similar, but sense is absolutely different. Self-contained hydraulic system serves a single consumer, that's enough. Independent hydraulic system may serve a group of consumers, and it is not connected to another independent system. So it's localization of leakage. In modern wood, it's possible to say all hydraulic systems are independent. Exceptions may be, but it is exceptions. Just in case of leakage in one system, must not be leakage from another system. Otherwise, you should do something by your actions, or you will have big problems. And the last one, it's working pressure. Hydraulic systems can be classified by working pressures. In the past, it is possible, small remark about dimensions. In this country, in Europe, they very widely use megapascal, or Pascal or megapascal. But in United States, in the past, it was another type of dimension, PCI, pound per square inch. So, which is why these figures are not so good in megapascal, but because they are integer in PCI. So 14 megapascal, it's approximately 2000 PCI. Such systems were used in old aircraft. Now it's difficult to find aircraft with such system. 21 megapascal, it's also old standard, but a lot of aircraft which were designed previous 10, 20 years use this standard, and it's possible to say that majority of flying aircraft use this standard. But it's possible to say it's also obsolete. 3000 megapascal, or 3000 PCI. 28 megapascal or 4000 PCI, it was an attempt to improve mass parameters, but only some aircraft apply this standard. It doesn't come widespread. And technology overrun with standard, and in the most modern aircraft you can find standard 35 megapascal or 5000 PCI. So such aircraft as Airbus 380, Boeing 787, it's just 35 megapascal. Так, I see that 13:15. Так, это у нас уже брейк. Или еще не брейк? Нет, еще не брейк, еще 15 минут. Okay, now let's discuss features of working fluids. So there are physical properties, and next real names of these working fluids. Density of working fluid, it is not so difficult, so critical parameter, but it's possible to say it's also important. The density of working fluid depends on pressure and temperature. Up to pressure of 30 megapascal, it's possible to use linear dependence of density of temperature, where alpha is temperature correction coefficient, and rho zero is density under normal conditions, so in the normal pressure. As for gas, in the pneumatic system, we will not have such paragraph, because what to say about air. Here it's possible to use two formulas. First, it's a gas law, pressure over constant R over temperature, absolute temperature. Or otherwise, to use parameters at normal condition. Density will be equal to density at normal condition, current pressure over normal pressure, standard normal temperature over current temperature. In this case, it's possible to recalculate density of gas. Of course, for gas, density will change far more sharply than for fluid. Viscosity. Viscosity is far more critical parameter. We discussed viscosity previous semester as for fuel, as for oil. Here it's possible to say almost the same remarks. Viscosity defines fluid drag against shear deformation, and it's possible to estimate it by two kinds of coefficients, by dynamic viscosity coefficient and kinematic viscosity coefficient. Dynamic viscosity, which is defined usually as eta or Pascal second, it's a friction force appearing on a unit area at unit velocity gradient. Coefficient of kinematic viscosity, which usually denoted as nu or meter squared over second, is determined as a ratio of the dynamic viscosity coefficient to density. So, for us, it's possible to say that viscosity is very important by first reason it is friction. Viscosity will define friction, and friction defines pressure losses in the system, one kind of pressure losses. And another, it is protection against wear, because with just fluid will be used inside actuators, inside hydraulic pumps as lubricant. And if viscosity will be very small, it's also bad, because it will be extruded and will be dry friction. So strong wear and very short service life. In the picture below, you can see dependence of absolute viscosity or dynamic viscosity versus pressure and temperature. Above, you see that it's possible to have a formula, linear dependence of kinematic viscosity from pressure. In the graph, you see the following. Horizontal axis is pressure, megapascal. Vertical axis is nonlinear scale, logarithmic scale, it's viscosity, dynamic viscosity. And here you see four sets of graph. Lines number one, this and this. It's a petroleum-based fluids which were used in the past, which are flammable at different temperature, 37, 65, and 93 degrees of centigrade. Lines number two is phosphoric acid ether. It's a liquid which is used to create fluid, but it isn't fluid. And lines number three is phosphate ester fluid. It's just inflammable fluids, with lines number three. It's the best from point of view of safety, from point of view of fire safety. But it is worsened because from the dependence of viscosity versus pressure. Of course, we wish that our fluid with parameters will be independent of pressure and temperature. Unfortunately, it is not so. Physical features, chemical features force us to use such liquids as is. One parameter, flammability, fire safety, we improve. Another parameter, dependence on pressure, we decrease, we make it worse. And lines number four, it's very old kind of hydraulic fluid, water ethylene glycol. With, you see, dependence on pressure was minimal, but with fluid have another big problem. It can be frozen under negative temperature, so it's impossible to use it in aviation. Fluid compressibility is defined by coefficient of volumetric compression, beta, or in other words, by elasticity model EF. It's inverted values, as you see. So it's a relative change of volume, so change of volume under pressure and without pressure over initial volume, and over this pressure difference. So with displacement, you can see with volume, modulus of elasticity, you can see in this graph. So with pressure increase, with elasticity model also increases. No, it's easy to imagine when you have some substance and you compress it, but it could not extend sideways. So of course counteraction will increase because distance between molecules will decrease. So it will be non-constant, it will increase. And right graph here shows you dependence of modulus of elasticity of real fluid over modulus of elasticity of fluid without air when it's really degassed. And you see that there are more gas content, there low will be modulus of elasticity. So compressibility of the fluid containing dissolved gas will increase. It's one of the idea why closed type hydraulic systems which insulate hydraulic fluid from any gas is preferable, because we increase modulus of elasticity and so we avoid compressibility of fluid. What is compressibility of fluid? You apply force to the actuator, but fluid in the actuator is compressed and doesn't perform required function. So it's of course very bad. We wish to avoid such situation, such case. Fluid degradation resistance defines fluid service life. What does it mean? Well, you buy new hydraulic fluid, you fill it to the hydraulic system, and you think it will be used all the time, 100 years. Unfortunately, it is not so, because when fluid passes through small gaps in some pressure regulators, in actuators, in some clearances, internal leakages. Fluid alone molecules, which are especially used to provide required viscosity, will be destroyed, mechanically destroyed. It's special additives, polymeric additives with very long molecules. Under high pressure, passing through small gaps, they will be mechanically destroyed. And with the time, viscosity of fluid will decrease due to this process. And it is assumed that when viscosity of the fluid decreased by 10% from initial value, we need to replace with hydraulic fluid. So it's will limit service life. It's one of the conditions for service life. Next, gas solubility in fluids. I just mentioned it. We discussed it in fuel system, discussed it in oil system. Here, the same problem because similar substance. Depending on pressure, 10 till 30% of total fluid volume, it is a dissolved gas. They are higher pressure, they are more with dissolved gas inside. So solubility of air in fluid is directly proportional to fluid pressure and inversely proportional to density, viscosity, surface tension of fluid. So it's also very bad, and it will provide compressibility. So to avoid this, we can use special deaerators. We can use closed-type hydraulic systems. You, of course, remember from fuel system how we discuss how we select altitude performance, how we select pumps by cavitation. Cavitation was a physical phenomenon which will limit altitude performance. So cavitation can take place even in hydraulic system. So we use displacement type pumps. They require very big cavitation margin. So inlet of the pump, it's a place of possible cavitation. So cavitation in this case can be rather harmful, can damage the pumps or pipelines, and so we must avoid cavitation. So to provide it, we must have enough overpressure in the hydraulic tank. We should degas hydraulic fluid, etc. As for desirable requirements for the hydraulic fluids, it's possible to mention the following. Optimal viscosity and minimal viscosity variation with temperature and pressure ranges. It's desirable. Unfortunately, real fluids will change viscosity with temperature very sharply. Yeah, I suppose you remember oil system when we consider it, so viscosity will change very sharply with temperature, unfortunately. Now you will see figures. High thermal and chemical stability, which provide wide temperature interval for operation. Unfortunately, this temperature interval is not so wide as we wish. So chemical destruction of the fluid will limit this interval. Anti-corrosion and lubricating properties. Why it's important? When we discuss oil system, we say its main property, its main function. Yes, what about hydraulic system? In hydraulic system, all the actuators, all the pumps will be lubricated by this hydraulic fluid. There are no special lubricant for pump, for actuator. Just the same hydraulic fluid which is used to pass power, it is a lubricant. So this hydraulic fluid must have good lubrication and anti-corrosion properties. So again, sometimes it may be contradiction with other requirements. Compatibility with rubber and sealing materials. It's also a problem. When we select fluids by its inflammability, by its stability to temperature, it's tuned to something synthetic. These components of hydraulic fluid usually becomes more active, chemically active, and not any rubber or sealant materials can be used together with such fluids. So must be more expensive corrosion-proof rubber or something else. Minimal density, compressibility, and gas solubility. It's desirable, but unfortunately it isn't so easy. Density of hydraulic fluid is comparable with oil density. It's more than fuel. As for compressibility and gas solubility, I said that is not so easy. High thermal conductivity and thermal capacity. What does it mean? What for? Why it's important? We don't say about heat sink, we say about hydraulic power function. But we must think also about others. What does it mean? Hydraulic pumps during operation will have friction. When it have friction, what to do? У меня 4-я пара. Здесь, скорее всего. Ну, не получится. Так, sorry. It's when hydraulic pumps is working, inside will be friction. When hydraulic actuator is working, also will be friction. This friction will turn some energy to temperature, to thermal energy. And pumps, actuators can be overheated. How to cool them? To use special air cooling? No, it's not effective. Just the same hydraulic fluid which is inside can be used and will be used as heat sink for these devices, which is why next will be heat exchangers. But it means the fluid must have good properties for thermal conductivity, thermal capacity, otherwise no cooling will be. So again, you see contradictions in requirements. Так, it's bell. Again, let's make a break. I will not create new meeting. We will continue here. It's 15-minute break.